Hey everyone, so now we're going to do a couple example problems where there are kinematics for non-constant acceleration. So let's start with problem 3 here. A particle of mass m, initially at rest at x equals 0, so these are called initial conditions, is accelerated by a force that increases in time as F equals some constant c times t squared. Determine its velocity, v, and its position, x, as a function of time. Okay, now first thing to say about this is that we have f as a polynomial in time. F is some constant c times t squared. So this is not going to be a constant acceleration, right? The only force that's acting on the object is this force that is changing in time. So that means that the acceleration will be changing in time as well. So the kinematic equations at constant acceleration will not help you with this problem. Instead, you're going to need integrals that we set up in the last video. So let's do this problem. So first, let's write down my givens. I'm given the mass. I'm given these initial conditions. It is initially at rest at x equals 0. So that tells me that the velocity at time t equals 0 is equal to 0 because it's initially at rest, and the position at time t equals 0 is also 0, right? It's initially at x equals 0. And it's accelerated by a force that increases in time as F equals c times t squared. And I am asked for v of t and x of t. So now, first thing to note, right, is that we're given the force as a function of time. We need velocity and position. These equations here are going to be the ones that will help us out, right? But first, we need acceleration as a function of time. Well, since F equals ct squared, and that's the only force acting on the object, it's also equal to ma. So I can divide both sides of this by m, and I have that acceleration as a function of time is c over m times t squared. So that's helpful. Now I can use this equation here, right, to get the velocity. So velocity, to find the velocity here, I'm going to take an indefinite integral of acceleration as a function of time over time, and then I will use the boundary values, or the initial conditions, to get the constants of integration. So let's try that. Velocity as a function of time is equal to the integral over acceleration as a function of time. Plugging in values, it's c over mt squared dt. And I can pull the constants out front. Okay, constants can always be pulled out front of an integral. So now I have the integral over t squared dt. And that is the integral over t squared dt is t to the third over 3. That's the antiderivative. And don't forget that I also have plus a constant. All right, now c over m is a constant value, and this constant here is an arbitrary constant. So note that I can multiply c over m through here, and I'll have, the first term is c over m t to the third over 3. The second term is just going to be some other constant, right? So some constant times some arbitrary constant is just some other arbitrary constant. So that would just be a different constant. Now, the last step to getting the velocity would be to figure out what is the constant of integration. I don't think there's ever going to be a problem that I will give you on a homework or on an exam where you're just going to leave an arbitrary constant in there. unless it's some kind of question about integrals on the homework. That's not really a physics question. So we do have a condition that will help us. Right? We know that the velocity at time t equals 0 is 0. So let's see if I plug the velocity time t equals 0 into the thing that I just found here. Right? Of course, the t setting t equals 0 means that first term will go away. We're left with just that second term. So this will just be equal to that constant. But we know from our initial conditions up here that that is equal to 0. So that tells us that this constant, the value of this constant here, is 0. We know that because of the initial conditions. So therefore, velocity as a function of time is c over 3m t to the third. Okay, so that was the velocity. Next, we're supposed to find the position as a function of time as well. So we basically repeat the same procedure because position is going to be the integral over velocity, the integral velocity over time. So I could take the integral of c over 3m t to the third dt. Okay, now I could do that same thing where this value, this constant multiple, can be pulled outside of the integral, and then I would have the antiderivative of that times, the constant multiple times the antiderivative of t to the third dt, and of course that would just be c over 3m times, now I'm going to have t to the fourth over 4, right, plus some constant value. Okay. And so I can again plug in my boundary values to get the value of this constant. Okay, I don't want to leave this in terms of an arbitrary constant. I want to find what that value is, and the initial conditions will help me do that. So if I plug in x at t equals 0, I will get that that is equal to 0. And plugging in x equals 0 into this here, that first term here will go away. Right? The second term will be left. So this thing here is equal to that constant. So I have just found out, right, that again, that constant is equal to 0. So that's good. Now I know that x of t is equal to c over 12m t to the fourth, right, because the constant of integration is 0. So I found the two things that I was asked to find, velocity and position as a function of time, under this given force law. Okay, let's go on to the next problem. So this problem is a little more interesting, a little more difficult. The speed of a bullet as it travels down the barrel of a rifle toward the opening is given by v of t is equal to, let's just write this down, it's one of the givens. V of t is minus 5e7. I use e as times 10 to the power t squared plus 3e5t. Okay, so that's the velocity as a function of time, where v is in meters per second and t is in seconds. Okay, so that's helpful. Let's remember to put the units back in when we're done. The acceleration of the bullet just as it leaves the barrel is 0. Okay, so now this one is my boundary value, right? I'm told the acceleration of the bullet just as it leaves the barrel is 0. Now I always like to write down my givens in terms of like symbols that can be used in our equations. So let's say the acceleration at t end, we'll call t end the time when the bullet gets to the end of the barrel. The acceleration at t end then is going to be 0. That makes sense, right? That if a bullet is shot out of a gun, the acceleration is going to be 0 by the time it gets to the end of the barrel, right? It'll be accelerating the whole way through as it travels here. By the time it gets to the end and it leaves the barrel, it's not going to be accelerating anymore, right? Then it will be traveling at a constant velocity in the one-dimensional case. When we're only considering the x velocity, the velocity would be constant once it gets out of the barrel. So we'll use t end to be the time it takes for the bullet to get to the end of the barrel. Okay. Part A asks, determine the acceleration and position of the bullet as a function of time when the bullet is in the barrel. So A wants A as a function of time and position as a function of time, right? Okay, well, let's do the easy one first. Acceleration as a function of time is just the derivative of velocity as a function of time. And since that's known to us, right, we can just take the derivative of this function here. So the derivative of this function would be, well, the constant multiple stays out front times, well, the derivative of t squared is 2t plus, then we have 3e5 as the coefficient, times the derivative of t, which is just 1, right? Because we know from the power rule, d dt, t to the n is equal to n, t to the power n minus 1. All right. So this one was not too bad, right? We have minus 1e8t plus 3e5. Okay, that's our acceleration coming from the derivative of velocity. Now let's get the position as a function of time. So the position as a function of time is going to come from taking an integral over the velocity. So now I'm going to have an integral over this. So I'll have minus 5e7 times the integral of t squared. So that would be t to the third over 3 plus 3e5 times the integral of t, which would be t squared over 2, right? Because the integral of t to the n dt is equal to t to the n plus 1 over n plus 1. All right. And last and very importantly, we also have a constant, right? Arbitrary constant. Okay. Now, here, the position as a function, so this is the position as a function of time, right? Notice that when I plug in x, say at t equals 0, that's going to be just equal to this constant because these two terms would be 0 here when t is 0. And there's no coordinate system given to me, so I'm free to pick whichever one I want. And what I want is the simplest one possible. Why don't we pick t equals 0, where the velocity of the bullet just starts out, and we might as well just call that x equals 0. Why not, right? Then our constant goes to 0. So we'll just set that to there. I'm free to pick whatever coordinate system I want. So then I have xt is equal to, so just multiplying the 1/3 and the 1/2 through, I have, this is minus 1.67 10 to the 7th t to the 3rd plus 1.5 10 to the 5 t squared. There. That's it for part A. I have my acceleration and position functions. Now, in part B, I am asked, determine the time interval over which the bullet is accelerated. All right, so I want the time interval over which the bullet is accelerated. In other words, the time interval over which the bullet is actually in the barrel. Okay. Now, earlier we had said, right, t equals 0 is when the bullet starts, and t end was what I called the time when the bullet gets to the end of the barrel. So all we need then to find the time over which the bullet is accelerated is to get that value, t end, right? So that is equal to t end. So thankfully, I have a formula for the acceleration as a function of time, right? And I also know that the acceleration at t end must be equal to 0, because I was given that in the statement of the problem. The second sentence says, the acceleration of the bullet just as it leaves the barrel is 0. So the acceleration at t end, the time when the bullet is leaving the barrel, must be 0. So I can plug t end in to this equation that I have here, right? And so I have minus 1e8 times t end plus 3e5 when just plugging in t equals t end. And I know that a at t equals t end is going to be 0, so I can then solve for t equals t end. So just very quickly then subtract 3e5 from both sides. If I divide by then 1e minus 1e8 from both sides, that would go away. So those positive signs would cancel each other out, and I would have that t end is 3e minus 3. Right. So t end equals 3e minus 3 seconds. Okay. So that's part B. Now, this is an important thing here, right? I wrote this thing down because I knew that this was going to be a boundary condition that I would need in order to solve the problem. Don't be afraid to write things down like this variable t end there, even though you don't know what it is. You have to be able to write down something and then solve for it, even when it's not one of the typical values that you're, say, asked for in the statement of the problem. You have to be able to insert those values in there and come up with some variable, and then solve for it in order to answer a lot of these problems. Okay, so that's part B. Part C says find the speed at which the bullet leaves the barrel. So that would be v, right, at t end. Well, v at t end is just, we know the velocity is a function of time, and we can just plug in the value for t end, which we already know. So minus 5e7 times t end squared plus 3e5 times t end. Okay. And if I plug 0.003, that would be 3 times 10 to the minus 3 into this. Then I will have that this is equal to, just plugging this into my calculator, about 450 meters per second. Right. Then in part D, I'm asked to find the length of the barrel. So what is the length of the barrel? Well, if x equals 0 corresponded to the starting point of the barrel, then x at t end would be the ending point of the barrel. and also, therefore, the length of the barrel. So I will just take this polynomial here, take that polynomial here, and plug in 0.003 seconds for t everywhere in this polynomial. I'm not going to write it out again, because you can plug in 0.003 seconds in for t into this equation here yourself. When I put that into my calculator, I get that this is about 0.9 meters. Okay, so I'm done. The problem is complete. Last thing to do is to just kind of do a sanity check. So let's just take a look at each one of these things in turn. Does this make sense? That the barrel would be a little less than a meter. Yeah, that makes sense. That's kind of a long barrel, but it's not unrealistically long. So that checks out. Does 450 meters per second, does that sound like a reasonable value? Well, a quick Google search shows that a 22 caliber rifle shoots at about 430 meters per second to about 550 meters per second. So 450 meters per second would be right in the middle of that range. Right, this was for a 22 caliber. So 450 meters per second sounds very reasonable. That works. Could the bullet really only be in the barrel for 0.003 seconds? Yeah, that sounds reasonable to me. It actually, I was surprised. I was expecting this to be something smaller than 0.003 seconds, right? The bullet doesn't stay in the barrel of a gun for very long. But that sounds reasonable to me. So this all checks out, passes my sanity checks. You'll have problems like this on your homework. Just follow the same kind of procedure where you're going to either use derivatives, right, to go in this direction, right, use d dt for that, or you're going to use integrals to go in this direction. When you use integrals, always remember that there's that arbitrary constant and look for the boundary values that you're given. Plug those boundary values into the function to get your constants of integration and remove that arbitrariness from the formulas that you derive. And that pretty much sums up the entire procedure. All right, good luck on your homework.